Hello viewers, in today's session we are going to discuss a problem related to finding out the shortest distance between two skew lines or non-coplanar lines, right? So here we are going to solve this problem where we are given the equations of two non-coplanar lines, and we have to find the shortest distance between these two lines, and also we have to find the equation of line of shortest distance and coordinates of the points where the line of shortest distance intersects the two lines, right? So although we have solved some problems related to shortest distance between two skew lines in our earlier videos, but here we are going to solve this problem, right? And here we can find out these three things, that is shortest distance, equation of line of shortest distance, and coordinates of the points where the line of shortest distance meets the two lines, right? So here we'll make use of the Cartesian method. So let us start. So let us denote this line by L1 and this line by L2, right? And we know that two lines are said to be skew lines or non-coplanar lines if they lie on different planes, right? So the non-intersecting lines are also known as skew lines. So here these two lines lie on different planes. For example, this line L1, it lies on this plane. Suppose this is the plane, and here we have the line L1, right? And we have the line L2 on a different plane. Suppose this is the plane, and here the line is L2, right? So these two lines are non-coplanar lines, that is the lines lie on different planes, and we have to find the shortest distance between these two lines. So let us consider this distance as the shortest distance, and the shortest distance is perpendicular to both the lines L1 and L2. And here this point is the point of intersection of the line of shortest distance with this line L1. So let us take this point as, say, A, and this point is the point of intersection of the line of shortest distance with this line L2. So let us call this point as B. So here we have to find the shortest distance, that is this length, that is AB, and then we have to find the coordinates of the point A and the coordinates of the point B, and moreover we have to find the equation of the line of shortest distance, that is AB. So we have to find here this length or this distance AB, and then the coordinates of point A and point B, and equation of the line of shortest distance AB. So here this angle is 90 degrees, and similarly this angle is 90 degrees. So AB is perpendicular to L1 and AB is perpendicular to L2. So now let us find out the coordinates of the general point lying on this line L1 and this line L2. So for this, what we will do, here we'll take the scalar lambda, and here we'll take the scalar mu, right? So here lambda and mu are two scalars or two real numbers. So the purpose of introducing lambda and mu is to get the coordinates of the general point lying on line L1 and L2. So from this line L1, we can now write x minus 3 over 2 is equal to lambda, y minus 4 is over minus 1 is equal to lambda, and z minus 1 over minus 1 is equal to lambda. So let us now solve these three equations for x, y, and z. So from here we have x minus 3 is equal to 2 lambda. Then we can write x is equal to 3 plus 2 lambda. And from here we have y minus 4 is equal to minus lambda, that is y is 4 minus lambda. And from here we have z minus 1 is equal to minus lambda, and z is equal to minus lambda plus 1, right? And from this line L2 we have x plus 1 over minus 3 is equal to mu. Then y minus 1 over 2 is equal to mu. Z plus 1 over minus 1 is equal to mu. So from here we have now x plus 1 is equal to minus 3 mu, that is x is minus 1 minus 3 mu. From here we have y minus 1 is equal to 2 mu, and from here we have y is equal to 1 plus 2 mu. And from here we have z plus 1 is equal to minus mu, and z is equal to minus 1 minus mu, right? So from line L1 we have x, y, z as 3 plus 2 lambda, 4 minus lambda, and minus lambda plus 1. Now for some particular value of lambda, this coordinate represents this point A, right? So the coordinates of the point A may be written as 3 plus 2 lambda, 4 minus lambda, and minus lambda plus 1. And similarly from line L2 we have the coordinates x, y, and z, and for some particular value of mu this coordinate represents this point B, right? So the coordinates of the point B are given by here we have minus 1 minus 3 mu, then we have 1 plus 2 mu, then we have minus 1 minus mu, right? So for some particular value of lambda, this coordinate represents the point A lying on L1, and for some particular value of mu, this point represents, or this coordinate represents this point B lying on L2, right? So here we have now the coordinates of point A and point B. So let us assume that the point A is say x1, y1, and z1, right? And this point B may be considered as the point x2, y2, and z2, right? So now our aim is to get the value of lambda and mu. So to get the value of lambda and mu, we have to find out the direction ratios of this line of shortest distance AB, right? So here we can now write the line of shortest distance like this, and here we have A, here we have B, right? And the direction ratios of AB can be obtained by subtracting the x coordinates, then y coordinates, and then the z coordinates. So here we have x1, y1, z1. Here we have x2, y2, z2. So the direction ratios of AB are given by x2 minus x1, y2 minus y1, and z2 minus z1, right? So the first step is to get the coordinates of A and B in terms of lambda and mu, and then the second step is to get the direction ratios of this line of shortest distance AB which is perpendicular to both the lines L1 and L2 by using this formula: x2 minus x1, y2 minus y1, z2 minus z1, where x1, y1, z1 and x2, y2, z2 are given by these numbers, right? So here we have x2 minus x1, so we have minus 1 minus 3 mu, and then we have minus 3 minus 2 lambda, then we have 1 plus 2 mu minus 4 plus lambda, and then we have minus 1 minus mu and plus lambda, and here we have minus 1. So let us now simplify these three numbers. So we have minus 3 mu minus 2 lambda, and minus 1 minus 3 is minus 4. Here we have 2 mu plus lambda, and 1 minus 4 is minus 3. And here we have minus mu plus lambda, and minus 1 is minus 2. So the direction ratios of AB are given by these three numbers. So now the direction ratios of line L1 are given by 2, minus 1 and minus 1. So here we have 2, minus 1, minus 1, and the direction ratios of line L2 are given by minus 3, 2 and minus 1, right? And direction ratios of AB are given by these three numbers. Okay, so now here we'll apply these two conditions. That is, first, AB is perpendicular to this line L1, right? And the direction ratios of AB are given by these three numbers, and the direction ratios of L1 are given by 2, minus 1 and minus 1, right? And we know that if two vectors or two lines are perpendicular, then the product of the direction ratios is equal to 0, right? So if the first line L1 has direction ratios, say A1, B1 and C1, and the second line say L2 is having direction ratios A2, B2 and C2, then the condition for perpendicularity of the two vectors or two lines is A1, A2 plus B1, B2 plus C1, C2 is equal to 0, right? So here we are going to make use of this condition when AB is perpendicular to L1 and AB is perpendicular to L2. So when we apply AB perpendicular to L1, then A1, B1, C1 are given by these three numbers, and A2, B2, C2 are given by 2, minus 1 and minus 1. So when AB is perpendicular to L1, we have this condition, and when AB is perpendicular to L2, we have this condition. So in this case, A1, B1, C1 are these three numbers, and A2, B2, C2 are minus 3, 2 and minus 1, right? So let us first frame an equation using this condition. So using A1, A2 plus B1, B2 plus C1, C2 is equal to 0, we have now 2 times this number, that is 2 times minus 3 mu minus 2 lambda minus 4. Then we have here minus 1 times 2 mu plus lambda minus 3, and then we have minus 1 times minus mu plus lambda minus 2 is equal to 0. So let us simplify it. We have minus 6 mu, then 4 lambda minus 8, then we have minus 2 mu minus lambda plus 3, then we have plus mu minus lambda plus 2 is equal to 0. So here we have minus 6, minus 2, and here we have 1. So this is minus 8 plus 1, that is minus 7 mu. And then we have here minus 4, then here we have minus 1, that is minus 5, and here we have minus 1. So this is minus 7, that is minus 4, minus 4, minus 1, minus 5, and here we have minus 1. So here we have minus 6 lambda is equal to, here we have minus 8, 3 and 2. So this is minus 5 plus 2 is minus 3. So here we can write minus 3 is equal to 0, right? So now we have this equation. So now applying this condition to this situation, we have minus 3 times minus 3 mu minus 2 lambda minus 4, and then we have plus 2 times 2 mu plus lambda minus 3, and then we have minus 1 times minus mu plus lambda minus 2 is equal to 0. So from here we have 9 mu minus minus plus, and here we have plus 6 lambda, then we have 12, here we have 4 mu, then we have 2 lambda minus 6, and here we have plus mu minus lambda and plus 2 is equal to 0. So this is 9, this is 4, and this is 1. So this is 13 plus 1, 14. So here we have 14 mu, and here we have 6 plus 2, that is 8. 8 minus 1 is 7. So here we have 7 lambda, and here we have 12. 12 minus 6 is 6. 6 plus 2, 8. So here we have this equation. So now using this condition, that is AB is perpendicular to L1 and AB is perpendicular to L2, we have two equations or two linear equations in mu and lambda. So the first one is minus 7 mu minus 6 lambda minus 3 is equal to 0, and the second one is 14 mu plus 7 lambda plus 8 is equal to 0. So let us now solve these two linear equations in mu and lambda to get the value of mu and lambda. So now let us write these equations as 7 mu plus 6 lambda is equal to minus 3, and we can write this equation as 14 mu plus 7 lambda is equal to minus 8, right? And we can now solve these two equations by method of elimination. So let us multiply equation 1 by 2. So here we have 14 mu, then we have 12 lambda, and here we have minus 6. So now we can solve these two equations by subtracting equation 3. We can call this equation as 3. So subtracting 3 from 2. So here we have minus, here we have minus, and here we have plus, right? So subtracting these two equations, we can cancel these two terms. 7 minus 12 is minus 5 lambda, and minus 8 plus 6. So we have minus 8 plus 6, that is minus 2. So we have lambda minus 5 lambda is equal to minus 2. So lambda is minus 2 over minus 5, that is 2 over 5. So the value of lambda is equal to 2 over 5. Now let us substitute this value of lambda in equation 1 or 2. So here we'll substitute this value in equation 1. So we have 7 mu plus 6 times 2 over 5, that is minus 3. 7 mu plus 12 over 5 equal to minus 3. So we can now write minus 3 minus 12 over 5, that is minus 15, minus 12 over 5, that is minus 27 over 5, and mu is minus 27 over 7 times 5 is 35, right? So the value of mu is minus 27 over 35. So now using the values of lambda and mu, we can easily find out the coordinates of point A and B, right? So the coordinates of point A can be obtained by taking lambda is equal to 2 over 5 in this coordinate, right? So we have 3 plus 2 times lambda, so we have 2 times 2 over 5. Then we have 4 minus 2 over 5 and minus 2 over 5 plus 1. So taking a lambda is equal to 2 over 5. So now we have here 3 plus 4 over 5. This is 20 minus 2 over 5. This is minus 2 plus 5 over 5. So we have now 5 times 3 is 15. 15 plus 4 is 19. 19 over 5. Here we have 18 over 5, and here we have 5 minus 2 is 3, so 3 over 5, right? So using the value of lambda is equal to 2 over 5, the coordinates of the point A are given by 19 over 5, 18 over 5, and 3 over 5. Now we can find out the coordinates of the point B by using the value of mu. So let us substitute mu is equal to minus 27 over 35 in this coordinate. So we have minus 1 minus 3 times 27. So here we have minus 27 over 35. Then we have 1 plus 2 times minus 27 over 35. And then here we have minus 1 minus minus 27 over 35. So now we can solve these numbers here. So we have minus 1 minus minus plus. So here we have 81 over 35. Here we have 1 minus 54 over 35. Here we have minus 1 plus 27 over 35. So now we have minus 35 plus 81 over 35. 35 minus 54 over 35, and minus 35 plus 27 over 35. So now 81 minus 35 is 46, right? So this is 46 over 35, and here we have 15 and 4, that is minus 19 over 35, and here we have minus 8, that is minus 8 over 35. So the coordinates of the point B are given by 46 over 35 minus 19 over 35 minus 8 over 35. So viewers, here the point of intersection of the shortest distance with this line L1, the coordinates of the point A are given by 19 over 5, 18 over 5, and 3 over 5. And the point of intersection of the line of shortest distance with this line L2, the coordinates of point B are given by these three numbers. So now we have here we have found out the coordinates of the point A and B. So let us now find out the shortest distance, that is AB, using the coordinates of point A and point B along with the distance formula. So now the distance AB can be obtained by using the distance formula. So here we can now write x2 minus x1 square, y2 minus y1 square, plus z2 minus z1 square, right? So we have now here x1 y1 z1 is 19 over 5, 18 over 5, and 3 over 5, and x2 y2 z2 are given by 46 over 35 minus 19 over 35 and minus 8 over 35. So we have 46 over 35 minus 19 over 5 square, and then we have minus 19 over 35 and minus 18 over 5 square, and then we have minus 8 over 35 minus 3 over 5 square, right? So let us now simplify this expression. So now here we can take 35 as LCM. So we have 46 minus, this is 5 times 7 is 35, and 7 times 19 is 3, and then we have here 7 plus 6, that is 13, and here we have again the LCM is 35, and then we have minus 19. Here we have 5 times 7, and then we have 7 times 8, here 6, and here we have 12, right? And then we have here 35 minus 8 minus 5 times 7 is 35, so here we have 21. So now we can write here uh, 46 minus 133 is minus 87, and here we have 35, and then we have here minus, this is 5, and this is 1 4, and here we have 35, and then we have minus 29 over 35 and square. So now we can write AB as here we have the square root and minus 1 square, that is it is positive, again here positive, and here again it is positive. So we have simply 87 square uh, over 35 square. Then we have here 145 square over 35 square, and here we have 29 square over 35 square. So now here we can take 35 square as the LCM. We have 87 square plus 145 square, and here we have 29 square. So now we can here write, see here 87 can be written as 3 times 29, right? So we have 3 times 29 square, and then we have 145, and 145 can be written as 5 times 29, and here we have a 29 square, so we can write it as 1 times 29 square, and here in the denominator we have 35 square, so we can now write here 35. The square root of 35 square is 35. So now we can write AB as here we can take 29 square common in these three terms. So we have 29 square, and here we have 3 square, then we have 5 square, and then we have here 1 square, or simply 1, and here we have 35. So now 29 square can be taken out from this square root sign. So we have simply 29 over 35, and here we have 9 plus 25 plus 1. So we can now write 29 over 35. Here we have square root of 35, that is 9 plus 25 plus 1 is 35. So the shortest distance between the lines L1 and L2 is given by 29 root 35 over 35. And we can also simplify this expression by writing it as uh, 29 over square root of 35, right? Because here we have 1 and here we have 35 raised to half. So using the laws of exponents, we can finally write the length of shortest distance as 29 over square root of 35 units, right? So this is how we can find out the coordinates of the point A and B, and the length of shortest distance between these two skew lines L1 and L2. So now let us find out the equation of a line of shortest distance, that is the equation of AB, right? So here to get the equation of line AB, let us find out the direction ratios of the line of shortest distance AB. So the direction ratios of AB are given by x2 minus x1, y2 minus y1, and z2 minus z1. So we can now make use of these two coordinates. Point A is x1, y1, z1. Point B is x2, y2, z2. So we have 46 over 35 minus 19 over 5. Then we have minus 19 over 35 minus 18 over 5, and minus 8 over 35 minus 3 over 5. So now we can simplify. We have already simplified this type of expression while finding out the shortest distance. So here we have 35, here we have 46, and here we have 133, and here we have 35, and here we have minus 19, and here we have 126, and here we have 35 minus 8 minus 21. So we have here minus 87 over 35, and here we have minus 145 over 35, and then we have here minus 29 over 35, right? So the direction ratios of AB are given by these three numbers, right? So here we can see that we can express this the direction ratios in the simplest form by multiplying these three numbers by 35 over 29, right? Because we know that if two lines or two vectors are parallel, then they have either equal direction ratios or proportional direction ratios, right? So multiplying these three numbers by 35 over 29, we have here minus 87 over 35 times 35 over 29, minus 145 over 35 times 35 over 29, and minus 29 over 35 times 35 over 29. So here we have now cancelled the common factors. Here we have 29 times 3, here we have 29 times 5, and here 29 and 29 get cancelled. So we have here minus 3 then we have minus 5, and then we have minus 1, right? And again, if we multiply all these three numbers by negative 1, we have 3, 5, and 1. So here, instead of multiplying these three numbers by 35 over 29, we can also multiply these three numbers by negative 35 by 29 to get the direction ratios as 3, 5, and 1. So the direction ratios of the line of shortest distance are given by 3, 5, and 1. So now the equation of shortest distance AB can be written as x minus x1 over A, y minus y1 over B, and z minus z1 over C, where A, B, C are the direction ratios of AB. So A is x2 minus x1, B is y2 minus y1, C is z2 minus z1. So we can also write the symmetric form of the equation of AB as x minus x1 over x2 minus x1, y minus y1 over y2 minus y1, and here we have z minus z1 over z2 minus z1, right? So here we have seen that the direction ratios of AB are given by 3, 5, and 1, and x1, y1, z1 is given by 19 over 5, 18 over 5, and 3 over 5. So we have x minus 19 over 5 over 3, then we have y minus 18 over 5 over 5, and then z minus z1 is 3 over 5 over 1, right? So this is the equation of the line of shortest distance. So here we can also write the equation of line of shortest distance AB by making use of this point B, that is x2, y2, z2, right? So here we can also write this equation as x minus x2 over A, y minus y2 over B, and z minus z2 over C. So we can also utilize this point B in forming the equation of shortest distance, right? So here we have x minus x2, x2 is 46 over 35, and here we have 3, and then we have y minus y2, y2 is minus 19 over 35. So here we have now plus 19 over 35 over 5, and then we have z minus z2, z2 is minus 8 over 35. So here we have plus 8 over 35, and here we have 1. So this is another form of the equation of line of shortest distance. So using this point A, we can write the equation of shortest distance in this form, that is in this symmetric form. And if we use this coordinate, that is the point B, then we can express the equation of shortest distance like this, that is this equation. So viewers, this is how we can find out the shortest distance, equation of line of shortest distance, and coordinates of the points where the line of shortest distance meets the two lines L1 and L2. And here it is very interesting to note that this line of shortest distance AB is perpendicular to both the lines L1 and L2, right? So now here we have the direction ratios of AB as 3, 5, 1, right? So we can here verify the condition of perpendicularity of two lines or two vectors. So if we take the dot product of 3, 5, 1 vector with the direction ratios of L1, that is the vector 2 minus 1 and minus 1, then we can see that we have 3 times 2 plus 5 times minus 1, then we have 1 times minus 1, so this is 6, this is minus 5, and this is minus 1, so 6 minus 5 is 1, 1 minus 1 is 0, right? So it implies that AB is perpendicular to L1, right? Because the product of these two vectors, the dot product of, or the scalar product of these two vectors is equal to 0. Similarly, we can verify the condition for AB perpendicular to L2. The direction ratios are 3, 5 and 1, and here we have the vector minus 3, 2 and minus 1. So we have 3 times minus 3, then we have 5 times 2, then we have 1 times minus 1. So this is minus 9, this is 10, this is minus 1. So 10 minus 9 is 1, 1 minus 1 is 0, right? So we can, this is how we can verify that the line of shortest distance is always perpendicular to the two lines L1 and L2 lying on different planes.